In this video, we'll introduce our first numerical algorithm for the course, and that's the bisection method. It's used to solve roots problems and can get us through the dead end that we encountered in the parametric analysis example last week. After studying this video, you should be able to identify and formulate a roots problem. Also, you should be able to explain how the bisection method works and use Matlab to implement the bisection method. So, consider the seemingly simple algebra problem e to the x minus x equals 2. Suppose we want to solve for x. So we might try and do that. We might isolate the e to the x by first moving the x to the other side. Then take the natural log of both sides. Simplifying the right-hand side, that just gives us x. But again, we have x inside the logarithm and outside the logarithm. We could try taking the exponential of both sides, but we are back where we started. And this is an example of an algebra problem, a basic algebraic expression that we cannot solve analytically. This is impossible to solve using algebra. But we can solve it by formulating it as a roots problem. We'll formulate it as a roots problem and turn to our first numerical method, that being bisection. To formulate something as a roots problem, we're just going to put it in the form f of x equals 0, and then we're going to solve for x. A roots problem is to solve for x. So in this case, we would have f of x is equal to e to the x minus 2. And now that would be a roots problem where we want to find x. So f of x equals 0. So let's look at one method to do that, and that's called the bisection method. And here's how the bisection method works. To the right here is a plot that I generated of that expression, e to the x minus 2 minus x. And so we can look at that plot and see there's two values of x where f of x equals 0. We see one value over here around -2, and one value over here a little bit greater than 1. So we know we would say we have two roots of f of x. And we can use the bisection method to zero in and find what either of those roots are. And here's how it works. We'll start with two initial guesses that bracket the desired root. So let's say we're going to go for this root near x equals 1. So we might say that those guesses are xl is equal to 0 and xu is equal to 2. So we're picking 0 and 2 as a lower, this would L for lower bound of our bracket, and U for the upper side of our bracket. And we can represent this as our initial bracket goes from 0 to 2. And then what we're going to do is we will divide the bracket in 2. So we'll divide the bracket in 2. We could define some xm as xl plus xu over 2. In this case, that will be 1. And then what we want to know is, well, which half of, now we have two new brackets, one between xm and xl, and one between xm and xu. And we want to know which bracket includes the root. And we can do a simple test, evaluate f at xm, and multiply that by f at xl. If that is less than 0, then the new bracket, the root falls between xl and xm. If it's not less than 0, the new bracket falls between xm and xu. And then we'll just continue doing this until the stopping criterion is reached. And recall from the error analysis video, that stopping criterion is reached. We have to define an approximate relative error. So our approximate relative error would be EA is equal to xm minus our previous estimate, all divided by xm, and we are going to iterate or continue steps 2 through 3, recalculating the bisection until our absolute value of EA is less than or equal to some stopping criterion. And so to see graphically what that's going to look like, we would see after our first bisection that the root falls between 1 and 2, so we would go to the upper half, and then we would bisect that again, and we would see that we are between 1.5 and 1, and we would go to the lower half, and then we would bisect that again, and again wind up in the lower half until we converge. So let's look at some Matlab code to implement the bisection method. So here's a Matlab script file to implement the bisection method for that function. First, we'll use an anonymous function to define the function that we're working with, the roots problem. And one thing to remember is it's always important to formulate that roots problem before you define this function. We have to have that formulated as a roots problem where f of x equals 0. Here we'll define the stopping criterion and our initial guesses. And just for starters, we'll just take our first value of the root to be the lower guess, the lower side of the bracket. And then we're going to use a for loop, and this is set up with a maximum of 50 iterations. If we haven't converged in 50 iterations, there might be something wrong. And we'll talk about those limitations and when things go wrong in a future video. So as we go through the loop, the first thing we want to do is define our old root estimate. So we'll define that as xr old. And then we'll do our first bisection to bisect the bracket. And then we'll calculate EA. And we will test to see which new bracket does the root lie in. So we'll generate our test just as I showed on the previous slide, evaluating the function at xl, multiplying that by a function evaluation at our current root estimate, which would be the middle of the bracket. And if the absolute value of EA is less than or equal to ES, we don't need to do anything more, so we'll break the loop, and that takes us down to display our results. If that's not true, we haven't converged, we'll use that value of test to define our new bracket. So our new bracket will either be between x root and xl if test is less than 0, or it will be between x root and xu if the test is greater than 0. If the test happens to be 0, that means EA is 0, and we just happen to land right on the root. And then the last section of commands here is to display the results. So let's go over to Matlab and we will test this out. Okay, so here we are in Matlab, and what I'm going to do is use the debugger to watch what happens in the workspace as this bisection method mfile runs. So I'll set a breakpoint here, and we will run the method. And as I step through, we see that we've defined the function, the other variable definitions, stopping criterion, and initial guesses, and here we'll enter the for loop and store the old root estimate, bisect the bracket, calculate EA, test, generate our test case to see which will be the new bracket, and check to see whether we've met our stopping criterion. Here we will generate our new bracket, and we see that test is greater than 0, so the lower end of the bracket will become our root value. So now we're moving to our next bracket, and if we look down in the workspace, we will see now XL equals 1 and XU equals 2. So now we're at the bracket between 1 and 2, and we're about to start our next iteration. So we'll go again and go through, generate another bracket, calculate EA, do the test, and we see now this time the test is negative. So we are going to the upper half of the bracket, sorry, the lower half of the bracket for the next iteration and end. And you'll see we'll keep going through here and try our test function and see which bracket contains the root. Again, we go to the lower half of the bracket. So now we are at a bracket between 1 for XL and 1.25 for XU. We'll continue stepping through, and we're at the 5th iteration. I'll step through a bunch, and you see it keeps going. You see our test value is alternating sometimes between positive and negative values. And you also see XL and XU as we go through are getting closer and closer together. Now here at the 8th iteration. And now I'm just going to continue, now that we've seen what's going on, to finish this off. And we see it took 21 iterations to converge. And the final value of EA that just got below the stopping criterion is 8.32 times 10 to the minus 7. And our root is 1.1462. And then the next thing we want to look at is how we can write this as a user-defined function that's more generally applicable and not only set up for this particular roots problem. So here's a function mfile to do basically the same thing, and what I've done here is instead of putting this in a script mfile that's only applicable to a specific roots problem, we now have a function mfile where the roots problem formulation comes in through an input, and that input would be the function handle for an anonymous function that's defined in a calling script. So here's the calling script down here, and here's where we define that function, and then we send that function handle to the bisect basic function along with the initial guesses, or the initial bracket. And then we see basically the same code down here. This is all the same as before. But what we've done is written this now as a more general function, and that will be what we usually want to do as we move forward in the class, is when we implement a numerical algorithm, we want to do it in a way that it can be applied to a variety of problems. And now this can be applied to any number of problems and used in multiple ways. And we will have an example of that in the next video. Before we get to that video, I want to talk a little bit about where we go from here. So future directions for root problems in particular. One, we want to develop some more programming skills and make this into a more robust function for implementing the bisection method. We want to do a few things. One, we want to make sure that there is, in fact, a sign change in that initial bracket. Because if not, then there's no root and the bisection method can't work. We also would like to allow the value of EA to be an input to the function, but we want to learn how to do that and still include a default value. That'll involve a new Matlab programming command that we'll bring into our toolbox next week. We also want to allow, using a similar programming command, the maximum iterations to be input and include a default. And we want to be able to handle an input function that includes parameters in the function. We saw in the mathematical models video that in general the mathematical models we're working with will include parameters. So we want a function that we write to implement a numerical technique to be able to handle those parameters. And we'll talk about how to do that in this future video. We'll also analyze the performance of the bisection method and really look at these key measures for any numerical technique. We want to know in general, when we look at any numerical algorithm, when does it fail? How can we rely on it? Is it generally applicable, or does it only work in certain situations? How efficient is the technique? We saw that the bisection method took 21 iterations to converge on an answer. How much quicker could it converge? Does that depend on the inputs to the method, or is that inherent to the technique itself? We'll talk about that. Also, how accurate is the bisection method? And we'll look at all three of those in a future video, as well as study some other root finding algorithms, Newton-Raphson method, secant method, and some built-in Matlab functions for handling roots problems. And that concludes this video.